All right, open up your book to section 10-5. We're on page 522 in your book. Title of this section is Analytic Geometry of Conic Sections. Our objective is, given the equation of a conic section, find the foci or focus, depending on how many there are. Find the directrices or directrix, depending on how many there are, and the eccentricity, and vice versa. So in the first part of this section, we talked about these terms here to get a little more familiar with each of our conics and what exactly these terms refer to. Let's take a look at those properties again and understand where those come from, and we'll take a look at a couple of examples as well. All right, start with the two foci or two foci properties. Again, this is the property that we saw in the first part here for an ellipse. It turns out that d2 plus d3 is equal to 2a. And for a hyperbola, it turns out the absolute value of the difference between those two is also equal to 2a. To prove these, the proof of the hyperbola is a little bit more difficult. So for each of these, we're going to prove the property for the ellipse and realize that there is a similar technique you can use to come up with the proof there for the hyperbola. But let's go through the proof here for the two foci or two foci properties there for the ellipse. To help us out here, what we're going to do is we're going to pick a point xy on the major axis. So I'm going to go ahead and label that. I'll go ahead and mark that point way over here on the far right, I guess. We'll label that point right here. That point right there is going to be our point xy. All right, so that's some point I'm marking there on my ellipse. Now let's mark a couple of other key points that we should know here. Hopefully recall these. That somewhere over here you have a focus, so I'll call this focus. And somewhere over here, equidistance, we have a focus as well. And then you can measure a couple of distances here. If you measure the distance from the center to the focus, if I measure that this direction, that would be this distance c. I can do the same thing over here and measure this distance on the other side of my minor axis, and that's also going to be c. So those two distances are equal to c. In fact, let's mark one other distance here. If I measure the distance from the center to that vertex, or that point actually is that distance is my major radius, that's a. All right, so now let's mark what the d2 and the d3 are equal to on my sketch. So d2, remember, is the distance between the point on our ellipse and the nearest focus, so that would be this distance right here is d2. And then if I measure the distance to the other focus, so that would be, just measure that horizontally here like this, that would be that distance d3. All right, now let's see if we can actually show this property here then. I guess first thing we should do is measure a couple of these distances that we need. I need d2, so let's write down d2 and see how we can measure that. If you look over on the right there, I've got this distance a marked and that distance c marked. It looks like that if I take the difference between those two, that would leave me with what d2 equals. d2 is equal to a minus c, in other words. All right, let's do the same thing with d3 here. Look at d3 and see how I can relate that in terms of a and c. So if you look at d3, d3 is the sum of actually these three things here. I've got c is part of d3. This c here is also part of d3, and then d2. So d3 I can write as the sum of those three things there. I can write it as d2 plus c plus c. I'll go ahead and write it out that way. Let's replace d2 with what it's equal to. d2 we just set up above was a minus c. And if I have, well, I guess I can write this as plus c minus, or plus c and plus c at the end there. Notice though that some c's are going to cancel out for us. In particular, you lose this one and this one, we'll say. So this turns out to be just a plus c, it looks like. So d3 is equal to a plus c. All right, so now let's see if this, what we end up with when I add those two together. I take and add the left side of this, d2 plus d3. d2 we said is equal to a minus c. And d3 we just found out was equal to a plus c. Well, look at there. The c's are going to cancel out again for us here. This minus c and this plus c, those cancel out, and you're left with just 2a. There's our property. D2 plus D3 is equal to 2a. Now, I picked a point here, a very special point, xy, just so that my calculations were a little bit easier, but using distance formula, I could have done the same thing and come up with the same result here. So I haven't quite proven it for the entire ellipse here, but I've picked a very simple point for us to do that with. All right, look at your Pythagorean properties. We talked about two Pythagorean properties, slightly different for the ellipse versus the hyperbola. A squared is equal to b squared plus c squared for your ellipse versus a squared plus b squared is equal to c squared for your hyperbola. Again, think about which one of those is the biggest one. That'll help you set this up properly. Since for an ellipse, your major radius is a, that's the largest one. It's going to be a squared is equal to the sum of the other two sides squared there. And then for the hyperbola, same story. The focal radius, you have to go the furthest out to the from the center there to get to the focus. So that's the largest of the three values there. And that's equal to a squared plus b squared then. All right, again, you can prove this for both the ellipse and hyperbola. The hyperbola turns out to be a little bit more difficult to prove for, so we are going to once again prove this for the ellipse. But a similar proof would get us the proof there for the hyperbola. Okay, so let's pick a point, x, y, and again, this time we're going to pick the point, the little hint that it gives us here to help us out with this, is to pick the point that's at the minor axis. So we're going to name this point x, y. And then if I mark my two foci here, I'll name this my focus on this side, and we'll mark this as my focus over here on this side. Then when I measure the distances between the focus and that point, if I measure this distance right here, this is what we call D2. If I measure the distance to the other focus, that's what we call D3. Turns out there, because I'm picking the point right on the minor axis, that those two are equal to each other. D2 and D3 are the same. But in particular, what I want to look at is this little triangle here that's formed. That I've got a triangle that shows up right here that I'm looking at. If I measure this distance horizontally, that's known as my focal radius, so that's C. If I measure this distance vertically, that is my minor radius, so that is B. There are two sides of this right triangle, so I know my Pythagorean property tells me that the sum of the two sides, two legs squared, is equal to the third side squared. I guess really what I need to do then is show that D2 is equal to A, it looks like, and I'll have my property here. So let's do that. If we look at D2, first of all, we know that if I add D2 and D3 together, I get 2A. That was the property we just showed there for an ellipse. D2 plus D3 is equal to 2A. And again, because of where I picked this point, I can show that D2 and D3 are definitely the same. Those are equal distance. I have an equilateral, I have an isosceles triangle that forms with those two blue lines there. So because D2 and D3 are equal to each other, I can replace. I'll replace D3 in the equation up above. So I can rewrite this as D2 plus D2 is equal to 2A. Again, that's because of the fact that D2 and D3 are the same. And so that means on the left there I've got actually two D2s is equal to 2A. And of course you can divide out the 2's then. The 2's will cancel each other out. And you end up with D2 is equal to A. And I guess if we want to finish this up there, if I know D2 is equal to A, I can label that on my picture over here. This is also equal to A. And so our Pythagorean theorem tells us that A squared has got to be equal to B squared plus C squared. There's our property. All right, let's take a look at the next two properties here, which is the radii and eccentricity properties. And again, we'll go through the proof of these. We'll go through them separately here, though. I've already proven the two over on the right in the first part of our notes So you can go back and look at those, but this is just on the right side there, the combination of these two properties we see on the left. So for an ellipse and a hyperbola, it doesn't matter which one of those two you're talking about, it turns out that C, your focal radius, is equal to your eccentricity, E times A, where that's A is either your major radius or your transverse radius, depending on the conic. And A, that is your major radius or your transverse radius, is equal to your eccentricity E times D, which is your directrix radius. So those are the two properties we have here, the relationship between our radii and our eccentricity for the ellipse and hyperbola. So let's go through and prove the first one here. And then we'll tackle the second one. So actually, we're going to do the second one first, I guess, is really what we're going to do, just because that one's a little bit easier to prove here. But let's mark this point xy at the major axis like we've done in the previous slide there. We were either doing it on the major axis or the minor axis. That's a nice point to pick there for us. So this point xy. And then let's measure a couple of distances here. Actually, let's mark a few things here first. Let's mark where our focus is at. We'll call this our focus. And let's mark a directrix in here. So we'll say the directrix is right here. So our directrix. And then we can measure a couple of distances here from that point to our directrix. That's the distance D1. That's how we name that. And the distance from that point to the focus, that distance is D2, which actually we just showed that D2 is actually equal to A, right? We did that on the previous slide. So this is actually equal to A. As long as I'm picking that point at the at the minor axis, that's the case. And I guess we should name one other thing here. I'll go ahead and mark it here that if you measure the distance from your center to the directrix, that's called our directrix radius, so that's actually what D equals. Well, that means that D is equal to D1 in this case. So D is equal to D1. And we have from our previous slide there that A is equal to D2. So we have a property that relates eccentricity with D1 and D2. So let's write that down. We know that D2 is equal to eccentricity times D1. And then just replace D1 and D2 with what we said they're equal to. D2 is A, so that's A is equal to eccentricity times D1, we said in this case, is D. There's our property. A is equal to E times D. All right, for the other property, something similar, but we're going to work with the point on the major axis this time. So let's mark that point. I'm going to call this point right here. We'll call him XY. And let's label a couple of things here. Let's again mark where our focus is at. So I'll say that my focus is right here. That's my focus. And let's go ahead and mark the directrix as well. The directrix would be somewhere about right here. There's our directrix. All right, and let's measure a couple of distances then. If I've got a point marked, we can measure the distance from that point to the directrix. I got to squeeze that in over here, it looks like. But this distance horizontally would be D1. And if I measure the distance from that point to the focus, that's this distance right here, that would actually be D2. All right, let's measure a couple of other things here that we know about our ellipse. If I measure from the center to the focus, this horizontal distance, we call that our focal radius, that's C. And if I measure the distance to my vertex, that's my major radius, we call that A. And if I measure all the way to my directrix from the center, that's our directrix radius, that's D. So it looks like I should be able to write D1 and D2 in terms of A, C, and D is what we're going to try to do. So let's see if we can do that. Let's write down what D1 is equal to. So D1 is equal to, it looks like if I take the difference between D and A, The difference between those would leave me with just D1. So D minus A, it looks like, is what D1 is equal to. Let's do the same thing with D2. Now D2 is, again, a difference here, but it's the difference between A and C, it looks like this time. If I take A and I subtract C off from it, I think I'll end up with D2. So D2 is equal to A minus C. All right, let's go back to the same formula here that we started with the previous proof there. That is that D2 is equal to your eccentricity times D1, and then just replace D1 and D2 with what we found they're equal to. So D2 is A minus C, and D1 we said was D minus A. And now let's simplify this. So I'm going to write this just as A minus C. I'll get rid of the parentheses on the left side. Really, they weren't needed, but on the right side, we did need to distribute this eccentricity through. So it's E times D minus E times A. And actually, from our previous work there, we showed that A is equal to E times D. Those two are equal to each other. So I could either replace one with the other and then subtract these out, or actually they'll just cancel each other out because of the fact that they are equal. A is equal to E times D. And now if we multiply through by a negative 1, I'll end up with C is equal to E times A. And right there is our proof of that last property there. All right. Let's try using these now in an example here. So look at example 1 there on page 529. They say to consider the ellipse 49x squared. I'm going to go ahead and write our equation down here. 49x squared plus 16y squared. 16y squared is equal to 784. 784. All right. It says for part A, sketch the graph and show the two foci and the two directrices. All right, so we're going to sketch this with our sketch this equation. Oops, switched slides there. We're going to switch our sketch this equation here. I think to help us sketch it, though, I think it'll be easiest if I get it into that center radius form. So let's do that. So to do so, we're going to divide by the 784 and then simplify. So let's write it first as 49x squared over 784 plus 16y squared over 784. And that's equal to 1. Again, remember the center radius form has this equal to 1. That's why we're dividing by the 784. And now take your calculator and check to see what happens when you simplify this. But 49 over 784, that should leave you with 16 in the denominator there. You can check that out. But 16 times 49 there should give you the 784. And then do the same thing with 16 over 784. That simplifies to 49, or y squared over 49 is equal to 1. Again, you can check that calculation out there on your calculator. We're almost to the center radius form. Let's just rewrite this one last time here, and let's write it as x over 4 squared plus y over 7 squared is equal to 1. That right there is our center radius form. And this is nice because this tells me exactly where the center of this conic is at. They didn't tell you, or they did tell us that this was an ellipse if we didn't know that to start off with, but it's an ellipse. Its center is at the origin then, 0, 0. And I also know then its x radius and y radius, or x dilation and y dilation. We now know those as a major and minor radius. The major is the larger one, so that's the 7. The minor is the smaller one, that's the 4 in this case. All right, so let's sketch this thing. So since the y dilation is larger, it's lying kind of more in the y direction here. It's stretched further in the y direction. So 1, 2, 3, 4, 5, 6, 7, 8, 2. Certainly, if you have a piece of graph paper, that makes this sketching a little bit easier. But even if you don't, you can count this out just on your paper, just like I'm doing, and get yourself a pretty decent sketch of this. So I know my major and minor radii here. That is, I know my x and y dilation factors here, so I should be able to sketch this pretty good. Let me draw this in a different color here, though. Let's sketch this in blue. And down here, oops, that's something about like this. There's our ellipse. Now they said to sketch in your focus and your directrices. I'm going to wait to do that in the next step here. We're going to find out the actual values of where these are at. I think that'll be a much better way to do this, to sketch those in once I know actually where they go. All right, they are not going to be just randomly chosen where they end up here. They are uniquely defined for this ellipse here. So let's do that. This was part A. Let's just sketch this. All right, so now for part B. Part B wants us to find the 4 radii. That is your major and minor radius and your focal and directrix radius. And they also want you to find the eccentricity. All right. The first two are really easy to find because they're given to us right here in this equation. Now that we've put this into the center radius form, my major radius A is the larger of these two denominators. That's the 7. And my minor radius is the smaller of the two. That's the 4. Real easy to find if you get it into that center radius form. That's the reason why we want to do that. All right, now the ones that require a little bit more work are going to be the other radii, but we can do that. Let's start out with, let's do the focal radius next. We'll just do these in order. So we've got A and B. Let's move on to C. So for C, the Pythagorean property is the one that we want to use to come up with it. So let's write down that A squared is equal to B squared plus C squared. And let's solve that for C, because we're looking for what C equals. C is going to be the square root, then, of the A squared minus B squared. And we know what A and B are, so let's just plug those in. So we have C is equal to the square root of, it's going to be 7 squared minus the 4 squared, which sounds like 49 minus 16 sounds like 33. So we end up with, this is the square root of 33 is our value for C. So we've got A, we've got B, we've got C. Let's keep going here. Oops. I need to find out what D is. You can decide whether you want to find D next or whether you want to find eccentricity next. One of the additional properties, though, that I gave you there on your sheet is a relationship between the A, C, and D. And since I know A and C, I could find out what D is equal to. That is A squared is equal to C times D. And so I could solve this for D. D is equal to A squared over C. And so now that I know what the D is A squared over C, A is 7, so that's 7 squared divided by C. We just found out was the square root of 33. So that sounds like 49 over the square root of 33 is what we get for D. All right, last thing for us to find then is our eccentricity. And actually, you got several formulas that you can pick from to help you find the eccentricity. I think there's probably three, maybe there's a fourth one, but the 3 properties for sure that we have that involves that eccentricity. I'm going to pick the one that's C is equal to E times A. No reason in particular why I'm picking that one. I'm just going to pick that one. But you've actually got several that involve eccentricity and the other radii. So you have several ways you can calculate this. But let's solve this for E then. So E is equal to C over A. And we know what C is equal to. That's the square root of 33. And we know what A is equal to. That was our major radius. That was 7. All right. Now they wanted, I'm going to go back to part A now. They asked us to come up with these 5 values here. And I'm going to use the value of C and D here to help me sketch what my focal radius, or sorry, what my focus should be at and what my directrix should be at from up above. But I'm going to grab my calculator to help me out here because I got this square root of 33 and I want to find a pretty decent approximation for those. So let's grab our calculator. And let's calculate the value of C. C we said was the square root of 33. So it's going to be 5.7 something, 5.744. I really just need 1 decimal to get a pretty decent sketch of this, but that's all right. We have that. And then for D, our focal radius was 49 divided by the square root of 33. That value we had up above there, and we get 8.529. All right, so that gives us 2 values to work with. Let me grab a picture of that. And we'll just paste it in here so we have that to work with here. In fact, I'll move it up here so I can see it. I'll move it in a second here, but there we go. We've got ourselves our values for C and D here. So now when I go back to my sketch, I can more accurately figure out where these are. Let's sketch the, or mark the focus first. C is equal to 5.749. So from the center, if I travel from the center, 5.7 units in both directions, I'll end up at the focus. So there's 1, 2, 3, 4, 5. So 5.7 is going to be, I'll say, somewhere about right here, looks like my focus. Do the same thing in the other direction. 1, 2, 3, 4, 5.7. We'll say it's somewhere around there. Those are my two foci. And now that I have the directrix, the radius, which is 8.5, I guess I need to get a couple more marks here on my graph. So we'll mark those. So if I travel from the center, 8.5 units, that'll get me to 8.5 will be somewhere about right here. That's a pretty good spot for the directrix. And down 8.5 units will give me somewhere around right here. That's a pretty good spot there for the directrix. Again, I would probably wait until you have those numbers so you get a pretty accurate sketch of where those are. Otherwise, I'm just guessing where to put those. Now I know exactly where they should fall. And let me just move this down here so it's not covering up my calculation there. Just move it over to the side here. Okay. If I make that smaller. Put it right there for me. All right, let's take a look at part C on this one. Part C, and we're not going to do all of part C, but I can at least show you the first step of part C. Part C says calculate y for x equals 3. So I'll go through that with you. And then it says show that the distance from the point xy that we come up with is one focus, to one focus is e times the distance to the corresponding directrix. This is just showing you that property that D2 is equal to eccentricity times D1. You kind of played around with that already in the first part of this. So I'm not going to go through calculating those, but I can at least show you how to find out the correct y value here for part C. You're going to go back to the original equation that they gave us, or you could actually write any one of the forms that they gave us here, but I'm going to go ahead and go all the way back to the original. So 49x squared plus 16y squared is equal to 784. And they're telling you to plug in x equals 3. So literally that's what you're going to do. Plug in x equals 3 here. So I've got 49 times 3 squared plus 16 times y squared minus, that's equal to 784. So I'm going to subtract the 49 times, what is that, 9? Maybe I'll write it that way for the moment, and then we'll figure out what that's equal to. So I've got 16y squared is equal to 784 minus the 49 times 3 squared. I can divide by 16 and then take the square root, and that will get me y. In fact, I'm just going to write it this way, and y is equal to, will be plus or minus, because I'm taking the square root of this quotient here. Again, it's the 784 minus the 49 times 3 squared all over the 16. Again, you're dividing by 16 first and then taking the square root, plus or minus that square root there. So you can punch that in your calculator and find out what that's equal to. That will give you a point xy. You can then use distance formula to find these different distances that they're wanting to calculate. You've already done that in part 1, so I'm going to skip over that for right now. And I think that's a little bit of a distraction from what we're trying to do. I want to be able to come up with our calculations for our 4 radii and eccentricity, or, like we're going to see in example number 2, example number 2 on page 530 gives us a description of a conic and then asks us what kind of conic it is, and what's the equation of it. So they tell you here that the eccentricity is 1.25. That tells me the conic I'm working with, by the way. And then it says that you've got 2 foci. You've got a foci at 6,2 and another one at negative 4,2. Okay, so that's what they've given us here. So the first part of this is identify the conic. All right, so identifying the conic. Well, to identify the conic, look at the eccentricity. Since the eccentricity is greater than 1, this tells me it's a hyperbola. All right, so that's the first thing, is I know that it's a hyperbola based on the fact that it's got an eccentricity that's greater than 1. And now that we know that it's a hyperbola, we can kind of give ourselves a rough sketch of this thing. Even though they've only given us a couple of pieces of information, I can use that to kind of come up with a decent sketch of what I've got to deal with here. So I know that my foci are at 6, 2, and 4, negative 4, 2. So let me kind of center this around the x-axis here, or the y-axis, I mean. So 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4. So there's negative 4. Here's positive 6, 1, 2. So I can mark where my two foci are at. They told me one's here, and they told me one's here. Okay. So I don't know exactly what my conic looks like here. I know it's a hyperbola, based on the fact that the two foci, though, are lying horizontally next to each other there. Tells me that the transverse axis must go right down the middle of this, crosses right at negative 2, or a positive 2. It means that the asymptotes of this must come through something like this. Not sure exactly where they're at. And it means that my hyperbola must be opening up something kind of like this here. Okay, so again, I can't quite sketch an accurate sketch of it, but I do have a rough idea right now what this thing looks like. All right, so with that, we can actually find, since we know a pair here, that is, we know the location of our two foci. Oops, I sketched that wrong, didn't I? Let me redo that. I sketched that as if it was the vertex. It's a focus. Let me try that again. Actually, let me just do this. Great. Let's sketch that again here. It's not the vertex. It's a focus. So the vertex would be somewhere over here, we'll say. And a vertex would be somewhere over here, we'll say. Again, I don't know exactly where they're at right now, but I have a rough idea of what this sketch looks like. All right, there's a better sketch of this thing. All right. With having the location of the two foci, I'm going to mark those in red here, actually. I can actually find the midpoint of those. If I find the midpoint, that actually will tell me where the center of this thing is at. So let's do that. Let's find the center. So HK, the center of this, is equal to, it's just the midpoint. So average the x's, average the y's. So it's going to be 6 plus a negative 4 divided by 2. And then average the y's. That's actually pretty easy because they're already averaged, right? 2 and 2. But what do we end up with? 6 and negative 4 is 2. Divided by 2 is 1. So this would give me a value of 1 for the x. And again, the value of y is already averaged for me, so that's 2. So at 1, 2 is actually the location of the center of this. So go over 1 and up 2. That's right here. It's actually the center. That's where my asymptotes actually intersect, is right there through the center. But that gives me HK. And now the only other thing I need to know is my transverse and my conjugate radius. But in order to come up with those, I'm going to have to do a little bit of work to get there. That is, I need to know what the A and the B value are. But I've got to do a little bit of work to get there. All right. First thing we can figure out is what C is equal to. Since I know where the center's at, and I know where the focus is at, this distance right here is C. Or that would be the same as this distance right here. It's also C. Those are the same thing. So if I just take the difference between those, that should tell me what C is equal to. So C is equal to, let's do the one on the right here. The location of the focus is at 6, and the location of the center was at 1. So 6 minus 1 is 5. That is, those are the x values where those are at. So C must be equal to 5. Since I know the eccentricity, I can use that to help me calculate what A is equal to. Again, look at your formulas to help you think about what is the process I got to go through to answer this question here. I found my center. I can easily find my focal radius because I was told stuff about both foci. And I have a property that says that C is equal to E times A. C is equal to E times A. Since I already know what C is equal to, I can use this, and I know eccentricity, I can use this to solve for A. A is equal to C over E. And they told us that the eccentricity was 1.25. We just found out C is equal to 5, so we have 5 divided by 1.25 is what we end up with. And of course, 5 over 1.25, that's a nice number. That's 4, right? So A is equal to 4. My transverse radius is 4. And now I have A and C, and when I have A and C, the Pythagorean property turns out to be pretty nice. Tell me find out what B is equal to. I know that C squared is equal to the A squared plus B squared. Remember, that's the property, the Pythagorean property for the hyperbola. The one for the ellipse is slightly different. I can solve this for B. B is equal to the square root of C squared minus A squared. And I know what A and C are equal to, so we can just plug those in. So that would be the square root of C, we said, was equal to 5. And A we just found out was equal to 4. So 25 minus 16 is 9 squared. That turns out to be pretty nice. This turns out to be equal to 3. So we have B is equal to 3. Now, we're 1 radii from answering, I guess, the rest of this here of what are all 4 radii, but we really don't need it to come up with our equation. But let's go ahead and find the last one here. Might as well, since we're this close. And again, you've got now a couple of different formulas you could use to help you answer this, but we know that A is equal to E times D. And so I can use that to solve for D. D is equal to A over E. And so A is equal to, in this problem, what did we say A was? A was 4. Eccentricity is 1.25. And so 4 over 1.25, I'll let you punch that into your calculator. You should end up with 3.2, I think is the number we're going to end up with there. We didn't really need that one for this problem, but nonetheless, we can come up with what D equals. All right, we have everything we need to write our equation then. Let's write our equation, which is what part A was asking us. Identify the conic and its equation. All right, so we have x minus h. I forgot what my h and k are, the 1 and 2. So x minus h. And then since this opens up in the x direction, that means it's the y part of this that's negative. That is, our transverse axis is horizontal, is another way of looking at that. And then it's going to be y minus 2 over something squared is equal to 1. Again, the transverse axis is horizontal. So that goes with our x's here. Our transverse axis, the a value we said was 4. Up there and grab that. And then for B we said was 3. That's our conjugate radius. All right, that's part A. Identify the conic and find its equation. And now for part B, it says sketch the graph showing the foci and directrices. You may first plot the conic parametrically or use a program like the one from the previous section. Well, we have all the information we need in order to sketch this, so we can actually sketch this now that it's in its radius form. We've done this a few times now. The center's at 1, 2. So I've got a center here at 1, 2. I've got a transverse radius of 4 units. This is at 1 and this is at 2, so we'll go over 1, 2, 3, 4, 5. And we can go the other direction. There's 1, 2, 3, 4. Oops, that's a negative 3. So the transverse radii tell me where the 2 vertices are at. And then if I look at the y dilation and the x dilation, that tells me the slope of my asymptotes. So I know that my asymptotes have a slope of 3 over 4. So if I go over 1, 2, 3, 4 units and go up 3, I guess I need to mark a few more points here, don't I? Here, marks. There's 1, 2, 3. So this is at 5, and then 1, 2, 3. This will be at negative 1. That should give me enough points here to get my asymptotes in here. So if I go over 4 and up 3, that gives me, and then go over 4 and down 3. This right here is the slope of my asymptote. Go over 4 and up 3 would be here. Over 4 and down 3 would be here. So this is the slope of the other asymptote. Again, this thing opens up in the x direction, and it's got the two vertices marked here. That's this guy right here and this guy right here. So we should be able to sketch this now. Something about like this and about like this. Again, if you look at the sketch we started off with, this is similar to the original sketch we had there, and we're able to fill in a little bit more detail, though, compared to what we had at the very beginning. All right, that right there is the end of that question and the end of this part of section 10-5.